excuse me, did, with the concept questions from last unit, both virtually or people in person, I think I asked you, and I don't remember, sorry, this week's kind of crazy just with everything that I've been trying to think about. Again, I'm not here Thursday, Friday, okay? So we kind of front-loaded stuff with circular motion yesterday. We'll do that again today. I thought I asked, did I ask you guys to go through the last questions of these? I thought I did, but I might not have. Oh, you left early, yeah. Okay. Did anybody, I guess, I'm happy to go through them, but does anybody want me to go through any of them that actually tried them? If you did not try them, we'll just go through them next week when I'm here Monday and Tuesday. Because I definitely want to front load today more with like going through stuff with circular motion. But if anyone did and would like to go through any of them, I'm more than happy to discuss them. And just so you guys know and are aware, I'm actually going to live stream this on YouTube as well. And so that way, like the notes, I'm not going to make a separate video. Like these notes are going to be recorded. So over the next few days, if you have questions, like you can access that. It'll be, you know, a lot longer of a video than what we're used to, but I think it'll still be useful for you guys. Yes. Which is funny. I did it same thing for AP Physics too last period, and I didn't realize like some people were actually on watching it live, like that were not part of the class, and like someone was asking questions. I didn't even realize like someone was typing questions in. Didn't even realize it till I like hit end stream. So, oh well. Okay. Did anybody have questions with this, or would we prefer just to go through circular motion stuff? Again, circular motion is very similar to what we're already talking about. Like it's talking about net forces. It's talking about, you know, setting up a free body diagram. So all that stuff I'm cool with continuing because I think it's continuing to help our understanding of forces. Did anybody either virtually? Yeah, Shreya, go ahead.
Can you go over the second part of 17 where it's asking us to find the displacement with friction?
Yeah. So, and it's asking, so how would the position of the crate change if the ramp was frictionless compared to if the coefficient of friction between the ramp and the box was 0.25? That idea?
Yeah.
Okay. So.
And the part where we have to do it mathematically?
Say that again.
The part and the part after when it says to find it mathematically.
Okay. So, yeah, absolutely. So the situation is you have a ramp, and then the idea is we're going to have a box slide down the ramp, right? And then we're going to try to put a crate. So here's our ramp. We're going to try to put a crate on the floor that this box can then land in. Yes? And so the idea is without friction, we're going to get a certain acceleration down the ramp. And that's going to be based on, you know, my force of gravity here, my normal force here, my perpendicular, and my parallel, right? So initially, so without friction, the acceleration is going to equal the force parallel divided by my mass, right? And from that, if I could find the velocity final, my initial velocity is 0, but I could do, you know, 2 times my acceleration times my displacement down the ramp. And if I square root that, that would give me my velocity final, right, on the ramp. And then I could figure out my displacement, this displacement. So this is displacement on the ramp. This is displacement in the air, right? Which that would be velocity final times time, right? And if I know this height here, I could find the time, right? Where the time is going to equal 2 times my change in position y over little g, square root, okay? That's, I mean, I'm shortcutting to a lot of the equations that we would use, but this is no different than what we've done for projectile motion, right? One-dimensional motion down a ramp. We solved for acceleration, and that's the acceleration I would plug in there, okay? That's the acceleration of the ramp, acceleration on the ramp. Trey, are you good with that?
Yeah.
Okay, so now when we have friction, so with friction then, the only thing that we do is we add another force here, my force of friction, right? So in this case now, my acceleration on the ramp is still going to be my parallel force minus my force of friction divided by the mass, okay? We know how to solve for force of friction. You know, force of friction is my coefficient times the normal force. So you're going to have to find the perpendicular component. That's my normal force. You know, I give you the coefficient of friction. So here's the idea, though. What's going to happen to my acceleration? It's going to be smaller because we're subtracting some frictional force. So this acceleration should be lower, right? Which means, again, if I'm using this equation, my final velocity on the ramp, this value is going to be less. I should be traveling slower at the bottom of the ramp with friction than I would have, right? Which then I could, my time in the air though doesn't change. I'm still in the air for the same amount of time because it's still the same height, okay? And then I could just solve for my displacement, you know, this displacement. This is displacement in the air. I could solve for that displacement by whatever my new final velocity was times whatever time I'm in the air. Shreya, is that good?
Yes, thank you.
Yeah, absolutely. So yeah, the problem itself is exactly the same. The only situation is I have to have friction, so I have to solve for my perpendicular to get my normal force, right? And so it's a few more steps, but essentially it's the same process throughout. This is the only thing that's going to be different. Cool with that? Other questions? Circular motion. Marker's draining. Okay. So circular motion, right? The idea, I have this weight that is attached to this string, okay? And what we're going to look at is, my first question is, if this string were to break, where's the most likely place it would break? It's going to break when the tension becomes too big, yes? And the strands can no longer hold it together, okay? So where is the location within this circle that is the most likely place for it to break?
Like the outermost.
The outermost? What do you mean by that?
Like it's more likely to break for the end.
Okay, so like, sure.
Oh, wait, you mean like?
Yeah, sorry. I mean,
down.
I mean like in the circle, like in the location in the circle.
Oh yeah.
Where is it most likely to break?
Probably down because you've got gravity and you've got the fact that you're like swinging it.
I feel like
There's two spots?
I feel like it could easily break if it comes down, but I feel like it could also easily break as it goes up.
Okay. So as it's going down or as it's going up? Yeah?
Maybe when it switches directions from like at the part where like
Well, it's always changing directions.
There.
Yes.
no, like from when it changes from
This is really. It's not super comfortable to have this paracord, which is not meant to be held by hand and swinging it. Let me ask this. As I cut off the circulation to my hand, which way is the string always pulling on the mass?
always towards your hand.
Towards my hand.
Yeah.
Yes? That is a centripetal force. It is a force pulling something into a circle. Okay? Which way does the mass want to go? Like, think about this. When the mass is here, which way is it going? No, it's not going up. It's going this way.
Yeah.
If the string were to break when it's here, the mass is going to go this way. Okay? Like when you throw a baseball, right? You throw a baseball and you release right here. Yes? Or like it's better because baseball's not like it's not like you throw a baseball like this, unless you're, I guess for cricket, yes, for cricket they throw the ball, the bowler throws the ball like this. But for softball, right, their arm moves more in a circular motion, yes? Where do they release the ball? They release the ball right here next to their hip, right? Because when it's here, and I'm trying to make it higher so the people, right? When it's here, which way is the ball going? That way. And if I no longer have a force pulling it into a circle, the ball, because it has inertia, wants to stay in whatever motion it's in. Yes? Okay? If I wanted this mass to go upwards, where should I release it? Where should I let go of it? When it's right here. Yes? Because here it's moving upwards, and if I release, it continues moving upwards. An object in motion stays in that constant motion. Yes? Okay, so let's do this then. Let's draw here's my hand. Let's do the mass for here. Well, that's a little big. Let's imagine our mass is here, 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 and then we'll do kind of an awkward one.
Mr. Ellis, the video is very blurry.
Very blurry. Okay, why don't you guys just hop over to my YouTube channel? Because I'm live streaming on there, baby. Can you guys stay on the meet so we can talk? So like you can talk back and forth, but like jump over to my YouTube channel, hit a like, hit a subscribe, right? Down in the corner, down there. And does that work?
I don't know what to think about this.
This is education in real life,
Can
baby.
you imagine if your kids stumble across?
Mr. Ellis, can you mute yourself here? Because there's like an echo with the YouTube in here.
Yeah. Yeah, is that better? Is that better?
That's better.
Awesome. Yeah, make sure you give it a thumbs up, It's on a different thing. Give it a thumbs up, Come on, there's no thumbs up. There's no thumbs up on here. Oh my god. Dude, I have one video that it's got 40,000 views.
Actually?
Yeah. 40K, man. It's literally how to make a line graph on Google Sheets.
Well, no wonder it's Google Sheets.
40,000 views, and someone just commented yesterday. Literally, it said, quoting, "Bro, how does this video have 40,000 views and only 287 likes?" And I responded, "That's what I'm saying." Right? I mean, they're kids, they're students, finding a way to make their physics or their science or I don't know, whatever project they're doing. Give me a like, Hit that thumbs up, baby. Hit a subscribe. We'll learn physics together. Okay. You are part of YouTube history right now. Okay. Here's my string. Okay. Let's do this. It's always pulling in a circle. So let's go right here. Let's go right here. what are the forces acting right here? This is my mass, right? Being pulled in a circle. What are the forces here?
Gravity.
Good. Gravity. Straight down. Yes? Tension. Which way?
Yeah.
Tension. Yes? Make this a little more square. All right. Where's my acceleration? Guess what? This is a centripetal acceleration, right? This is a centripetal force, right? Oh, actually, I don't want to write TC there. Sorry. This is tension. Tension, though, is my centripetal force. It is the force that is pulling it into a circle. Okay. So there's no other forces here. Gravity is not affecting its like inwards. So in terms of some force is circular. Yes. The sum of the force is circular. Is just tension equals mass times acceleration centripetal. Okay, or circular. So then, and if we recall, remember AC is VT squared over R. Okay? And so the tension here is just velocity. M VT squared over R. Yes? I apologize, there's a little glare. Nick, can you try closing that blind for me and see if that helps that glare? That's right there. Not really. See if that one helps. See if that one helps.
There.
That's better. Cool. Okay. You guys good with that? So let's call this position. Let's call this position A. So this will be the tension at A. Is that? Okay. We'll say I was going in a clockwise rotation. So my velocity, tangential velocity is downwards in this case. Okay. All right, let's do position B. We'll have it be right here. What are my forces now?
Still gravity.
Okay, gravity's still down. Good.
Still have that tension.
Tension, though, in this case is up. Yes? And so now, the sum of the forces that are in centripetal, yes, that are acting, in this case, now we have tension minus the force of gravity, yes, equals mass times, I'm just going to skip ahead, velocity tangential squared over R, right? And even though it's not, we're saying R is constant for each of these. So let's just solve for tension then, right? Solve for tension. What is tension equal? We need to get gravity to the other side, right? So in this case, the tension is mass times velocity tangential squared over R plus my force of gravity. Thank you for that one like, whoever gave me a thumbs up. Appreciate that. Let's keep that going, guys. All right? I get 9 likes for the 9 people that are on here. I get a bonus point.
I'll take that.
So let me ask, what just happened to my tension force? It increased.
Yeah.
Yeah? It increased. Not only are we keeping the weight in a circle, but we're also fighting against the gravitational force. Yeah? You guys go with that?
Yeah.
Let's go to C. We won't go in order. We'll just go to C. Here, what do we got? We got gravity.
Ooh, tension.
All right, up to 3 lights. Keep it going, guys. We got tension here, yes? Okay, now what are the sum of my forces?
Is it going to be
In the centripetal motion, yes? Now it's, let's just do it for this one. Can we say down is positive?
Yeah.
right? Like let's just say down is positive. It's just going to make it easier, right? So it's tension plus the force of gravity equals mass times Vt squared over R. It's all for tension. M Vt squared over R minus the force of gravity. It's less. Yeah? It's smaller. The bottom's the highest tension. Right now, let's go to D. We won't solve this because it gets a little bit ugly, right? Everyone good that my tension is here? Yes? My gravity is down, okay? And here's why it gets a little ugly. So I'm going to say that like my XY axis is this way now. Yes? And so there is like some component of gravity that's pulling it in a circle. And there's also some component of gravity that's pulling it like this. Yes? We'll call this, the tangential force, and we'll call this the, I don't know. I've never done it like this. F gravity radial. Yes, the radial force. Okay. And so do you guys see how, like, look, slowly the tension force is going to get smaller. Yeah. Yes? And look, as something is moving this way, gravity is going to be trying to slow it down a little bit. Yes? And then as it goes this way, the component of gravity is going to be speeding it up, right? Gravity is going to be going away from the tangential, right? So from the tension. So the tension force is going to slowly get bigger, right? And it's going to slowly speed up, right? And that makes sense. If I just swing this and don't try to keep it at a constant velocity, right? It's slowing down on the way up, and then it's speeding up on the way down. Slowing down, speeding up, slowing down, speeding up. And if this is doing this, where's the hardest to hold on to it? At the bottom, right? Because that's where my tension becomes the greatest. Okay? What questions do we have?
What's the reason you have force of gravity T like on the from the string to the
Because let's do this color. This is my velocity tangential. Yes? So gravity now is doing two things. This component of gravity is pulling it into a circle, which is why my tension decreases. This component of gravity, look, my velocity is this way, my force is this way. Yes? What is that causing it to do? If I'm moving this way and someone pushes me the other way, what are they going to do to me? Slow me down. Slow me down. As I move up to the top of my circle, gravity is slowing me down. It's slowing down the tangential velocity. The tangential component of gravity is slowing down the tangential velocity. Yeah? As I come over here, right, now my velocity is here, my velocity tangential, and look, my tangential force of gravity would be here. Now this would be Ft of gravity. Yes? What's that going to cause the fall or the? Does that make sense? No, it's okay. I've never done that. That's really cool. I've never shown that, but it makes sense in terms of how that's worked. Questions? People at home, either type them in the YouTube live chat or unmute yourself. Right? What questions do we have? R is radius. Yes. Distance from the center.
So this is only for constant velocity?
This is assuming that our velocity is constant around the circle.
Because otherwise it just be like a pendulum, right?
What do you mean?
If the velocity is not constant, then it becomes more of a pendulum problem, right?
A pendulum problem?
Yeah, like if you have something that's like swinging back and forth. Like,
Wait, wait, this is, yeah, it's just gonna say no, change direction.
Yeah, I mean, if we have, that's a great question. So if we have, if we have this, we have a pendulum, right? Yes? In terms of this, you could either be moving this way with your velocity or this way with your velocity, it doesn't matter. Which way is your tension? Up. Yes? Still going to be the biggest tension is right here. Right? In terms of this, we're either stopping or we're starting to move back this way. Yes, I still have a tension here. Okay? And this is exact perfect question. This is exactly what I wanted to go into next. Velocity here when we're going back. Yes? Gabe, I mean, you the man. Okay? Tension here. Look, guys.
more or less.
Velocity tangential and force centripetal. The force pulling it into a circle. Yes? And the velocity tangential must be what? What's their relationship? There you go. You want to pull something into a circle, you better apply a force perpendicular to its velocity. Okay? You apply a force perpendicular to its velocity, you're going to pull that into a circle. As long as you continue to move or to apply that force perpendicular to its velocity. Okay? For circular motion to be true, for circular motion to occur, the force centripetal must be perpendicular to the object's velocity. It's got to stay that way, right? If you got some, like, think about this. You got someone running, I don't know why, this is the image in my head right now. You got someone running across like a balance beam, yes? And then you bring a ball and you hit them like this, yes? They're running this way. They have some velocity this way, right? And if you hit them perpendicular to that, it's going to knock them off the beam, right? It doesn't affect their forward velocity, but it now gives them a different direction, yes? If we were able to like continuously hit them perpendicularly, right, then you would essentially pull them into a circle.
Oh, yeah.
Okay, you would pull them into a circle. I don't know why. It's like that's what's in my mind.
I want to try. Please.
It's like old American. You guys don't even know American Gladiators, like old school American Gladiators.
That's like the routine. I think they like did that exact example, but it's like routine. They like usually jump off onto it and then they just get in the circle.
All right, another example. Draw this. This is a car.
Not as good as my horse.
No, it's not. It's way better. Okay, so here's a car. This is a top view of a car, right? So we're a bird looking down on the car. Okay, everybody cool with that? So it's going to be really hard to show gravity and normal force. Gravity is like into the board. Normal force is sticking out of the board, right? So if there were forces of gravity and normal force, like they'd be like this. Okay, gravity's in, normal force is out. When you get to AB Physics 2, I'll show you how to demonstrate that. Okay. What other force though? If the car is going around a curve, what other force is there? Yeah, there is. If it's going in a circle, there has to be a force pulling it inwards. Yes. What is the force that's pulling it inwards? No. There is no tension, right? You don't drive around with a string attached to your car pulling you. It's like, okay, roundabout, throw the lasso. Yeah. Gabe's like sticking out the side of his car. Okay, one rows to the roundabout. I got the lasso. Hey, I love it. Hey, I hope you know we're having fun. Okay. Yeah. What's the force, Gabe? You said it. It's friction. Yeah. Guess what? If there's a patch of ice here. There's a patch. Well, I don't know why we have red ice. Right? If we had ice here.
You crashed your car?
I'm never.
Guys, think about it. If there's a patch of ice there, what does ice get rid of? Friction. And so you keep going forward because you're already going forward, yes? So in terms of this, there is a centripetal force of friction. Yeah, we're not encouraging drifting here.
No.
Okay?
When you overcome friction.
But guys, look, here's my force of friction, yes? Here's my velocity. Velocity tangent, that's awful. Velocity tangential, yes? Again, normal force, like gravitational force, they're there, we just, bird's eye view. Yeah? Okay, let's do this. Find max velocity a car can go around the curve. We don't like that, yes? Guys, come on. Sum of the forces and the centripetal, yes? Force of friction. Yes? If it's going in a circle, it's accelerating. Which way is my acceleration? Inwards. Which way does it feel my body wants to go? Because your body has inertia, and it wants to keep going whichever way it was going. That's why you get thrown out, because you're accelerating in. Right? Okay, so this is MA, but it's an A centripetal. It's a centripetal acceleration. Okay, let's keep going. The force of friction equals mvt squared over r. Okay? Solve for Vt. Vt equals force of friction times r divided by mass, square root. Guys, we understand how I'm getting here? Divide by mass, multiply by r, square root. Okay? Look, we're in a problem without numbers. And it's beautiful. Right? The numbers are arbitrary. If you know this process, it doesn't matter what numbers the problem gives you, you can do it. Right? Because the numbers don't matter. Okay? Let's keep going. What's the force of friction? That's the coefficient of friction times the normal force times r divided by my mass, square root. Yeah, sorry. I don't, you're important, but not as important as my live stream here, okay? Still only 4 thumbs up. Pathetic, guys, pathetic. People are bouncing like, I can watch this anytime. All right, let's keep going. Let's keep going. Velocity tangential, maximum, yes? Because here's the thing. It's as big as a force as I can get, because once I go faster, my frictional force can no longer hold me, okay? Because frictional force is dependent upon the coefficient of friction and the normal.
Wait, is that why, like, you can, use traction and you go around a turn too fast?
Yeah. Because the desire of your car to keep going is greater than the frictional force can pull it into a circle. So I slow down, all right?
Something tells me he's thinking, so this is how I can drift.
Yeah,
No,
pretty
it's
good.
not.
Slow the heck down. What's up?
The velocity tangential is our maximum velocity.
This is your maximum velocity. This is going to be equal to frictional force, yes? Okay? Here's the thing. If this velocity is just a little bigger, it's now bigger than frictional force. So, the idea is frictional force must be greater than or equal to this number. Yes?
Yeah.
Frictional force, though, is dependent upon mu and Fn. You can't increase it, right? So, this is the idea that this is the maximum that I could go. Okay. Well, last thing here. Coefficient of friction. Normal force is gravity, mg. Yes. Gravity and normal force in this case are equal. R over m. Square root.
Yeah.
what happens? Simplify. Mass goes away. What? So my final answer is that velocity maximum is the coefficient of friction, gravity, the radial distance of my turn. I don't know why I underlined it. Square root. That's as fast as the velocity of an object that can go, right? How, when you're going around a curve, is there a like suggested speed limit? Yes? How do they know what speed you should be going? Well, guess what? Why does it not depend upon like if you're a truck or if you're a sports car? Well, because guess what? The mass doesn't matter. Now, are they going to put that suggested sign right at the actual maximum value? No, because there's idiots like all of us, right? Oh, it says 25, I'm going to take it at 30. Right? Yeah, 10 over, you can handle that, right? But they're going to put it lower than what it actually is. Yes? Question?
So
now, be careful because like big trucks have higher center of masses, right? And so like, and this is just for their wheels to not slip, right? For their wheels to maintain constant friction, this is what has to be true. Okay, yes, profiles of vehicles are very different, right? If every vehicle was a physics perfect vehicle and like its mass was a flat mass, right? That didn't have like, so there's issues,
so
right?
it's entirely different for tipping.
Yeah, come on. This is just, no, it's okay. This is just an object driving around a circle for the wheels to not slip, right? This is for the wheels to not slip, okay? For the wheels to not slip. Ooh. Let me ask this. You got a tire.
Okay.
You got a tire driving on the ground, yes?
Yeah.
Is that static or kinetic friction?
If it's driving, it's kinetic.
Is it?
Well, I guess there's.
It is moving, yes? But let me show you this. I don't know what I just drew there. Like this sliding across the ground is kinetic. Yes? Is your tire sliding across the ground?
No.
No. It's rotating, yes? Guess what? You don't want it to slip. Yes? You don't want it to slip. It's stationary on the ground, yes? Like the bottom of here, when it rolls, is not sliding. Yes? It's not sliding, it's rolling. So when something is rolling, what type of friction is that? It's static. Yeah. This is static friction. Is rolling. Okay? Have you ever watched NASCAR? I mean, maybe. Dublin, so probably not. If you've watched NASCAR, like when they win, what do they do to their wheels? They spin them. Yes? Once the wheel is slipping, that's kinetic. And what has just happened to our friction? It's gone down. Yes, so it's now easier to have our wheels slide. Okay? Yesterday we went through examples of like going over or on bottom of a hill. Yes?
Yes.
Going on top of the hill, going bottom of the hill. It's the same as the tension. Right? It's very similar to the tension. Okay? Around a curve. Like, do we see it's still just our net force? The big thing is if your net force is perpendicular to your velocity, if your force is perpendicular to velocity, then it pulls it in a circle. Right? That's the big thing with circular motion. There's another concept I want to add to it, but we're not going to do it because it's just too much. Okay? Questions? People at home, questions?
Wait, so when it was going,
You're not at home. I'm just joking. What's up?
when it was going up and down the hill, what's
Yeah.
the force there? Is that still friction?
Yeah, let's just do it real quick. No. No friction. Gravity.
Oh.
Here's the idea. Top of a hill,
Yeah.
gravity, normal.
Oh, yeah.
Yes?
Hey.
Gravity normal, okay? So what is the pulling in a circle? Gravity. So the sum of the forces centripetal is, it's like normal minus the force of gravity equals mv squared over r. Okay? And what we said here is that my normal force, we said the normal force is less than the force of gravity because it's the sum of the forces that pull it in a circle. And so this is why when you go over top of a hill, you feel weightless. Because your normal force is your scale, yes? And if your scale goes down, you have that sensation of weightlessness, right? When we're at the bottom of a hill, now we still have gravity, we have normal, right? It's now this same idea, but now my normal force is greater than my force of gravity because it has to pull it into a circle. Yeah? And so if my normal is bigger than gravity, now I have that sensation of heavier weight. What's that?
Is that why we use tangent? Wait, you know what I'm talking about?
No. Okay? Good?
Yes. they
Yeah. Sorry if that was something that you weren't there for yesterday. I know there was a few people that are on our call today that weren't there yesterday, so that's good for them as well. People here good? Guys, over the next 3 days, I'll just give you questions to work through. Okay? It might be just old physics, or not old physics, old forces questions, as well as some circular motion stuff. Okay? Next week, we're going to have our midterm Thursday and Friday. Okay? I'll be back Monday, Tuesday next week, so we'll have that chance to go through stuff. But just, make sure we're respectful to the sub. People, if you're virtual, you do not have, there's no live stream. Okay, there's no live stream Thursday, Friday. I will be on tomorrow at home. If you have questions, like anybody, whether you're RLA or not, if you want to pop in and ask me a question, I'm not going to do a lesson. It's just more of like, I have a question on this problem. Can we go through it? So that's the plan for the next 3 days. Okay.
What's the format of the midterm?
Midterm's going to be 2 days now. It's going to be first day, all multiple choice, 25 multiple choice questions, everything we've covered this year. Second day is going to be 2 free responses. Okay. We'll then come back Monday. We'll do our group test on Monday. Okay. You guys can head off here and virtually. You guys can head off. If you have questions, feel free to stick around. I'm going to stop my live stream. Thanks for the 5 thumbs up. Make sure you subscribe. No TikTok.
No TikTok.
Oh, wait.